Chapter 5. Gravitation. Exercises pages 97 to 99. Exercises Q1. Page 97. Choose the correct option. The value of acceleration due to gravity is maximum at underscore 1. The equator of the Earth 2. The center of the Earth 3. The pole of the Earth 4. Slightly above the surface of the Earth. Solution. The value of acceleration due to gravity is maximum at the pole of the Earth. Exercises Q1. Page 97. Choose the correct option. The weight of a particle at the center of the Earth is underscore 1. Infinite 2. 0 3. Same as that at other places 4. Greater than at the poles. Solution. The weight of a particle at the center of the Earth is 0. Exercises Q1. Page 97. Choose the correct option. The gravitational potential due to the Earth is minimum at underscore 1. The center of the Earth 2. The surface of the Earth 3. Points inside the Earth but not at its center. 4. Infinite distance. Solution. The gravitational potential due to the Earth is minimum at the center of the Earth. Exercises Q1. IV page 97. Choose the correct option. The binding energy of a satellite revolving around the planet in a circular orbit is 3 times 109 J. Its kinetic energy is underscore 1. 6 times 109 J. 2. Minus 3 times 109 J. 3. Minus 6 times 10 plus 9 J. 4. 3 times 10 plus 9 J. Solution. The binding energy of a satellite revolving around the planet in a circular orbit is 3 times 109 J. Its kinetic energy is 3 times 10 plus 9 J. Exercises Q2. Page 97. Answer the following question. State Kepler's law of equal areas. Solution. Statement. The line that joins a planet and the Sun sweeps equal areas in equal intervals of time. Exercises Q2. Page 97. Answer the following question. State Kepler's law of the period. Solution. Statement. The square of the time period of revolution of a planet around the Sun is proportional to the cube of the semi-major axis of the ellipse traced by the planet. Exercises Q2. Page 97. Answer the following question. What are the dimensions of the universal gravitational constant? Solution. The dimensions of universal gravitational constant are L3m1t2. Exercises Q2. IV page 97. Answer the following question. Define the binding energy of a satellite. Solution. The minimum energy required by a satellite to escape from Earth's gravitational influence is the binding energy of the satellite. Exercises Q2. Page 97. Answer the following question. What do you mean by geostationary satellite? Solution. Some satellites that revolve around the Earth in the equatorial planes have the same sense of rotation as that of the Earth. They also have the same period of rotation as that of the Earth, i.e., 24 hours. Due to this, these satellites appear stationary from the Earth's surface and are known as geostationary satellites. Exercises Q2. Page 97. Answer the following question. State Newton's law of gravitation. Solution. Statement. Every particle of matter attracts every other particle of matter with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Exercises Q2. Page 97. Answer the following question. Define the escape velocity of a satellite. Solution. The minimum velocity with which a body should be thrown vertically upwards from the surface of the Earth so that it escapes the Earth's gravitational field is called the escape velocity (v) of the body. Exercises Q2. Page 97. Answer the following question. What is the variation in acceleration due to gravity with altitude? Solution. Variation in acceleration due to gravity due to altitude is given by gh equals acceleration due to gravity of an object placed at h altitude. G equals acceleration due to gravity on the surface of the Earth. R equals radius of the Earth. H equals attitude height of the object from the surface of the Earth. Hence, acceleration due to gravity decreases with increase in altitude. Exercises Q2. X page 97. Answer the following question. On which factors does the escape speed of a body from the surface of Earth depend? Solution. The escape speed depends only on the mass and radius of the planet. Exercises Q2. X page 97. Answer the following question. As we go from one planet to another planet, how will the mass and weight of a body change? Solution. 1. As we go from one planet to another, mass of a body remains unaffected. 2. However, due to change in mass and radius of planet, acceleration due to gravity acting on the body changes as g proportional mr2. Hence, weight of the body proportional also changes as w proportional mr2. Exercises Q2. Sheet page 97. Answer the following question. What is periodic time of a geostationary satellite? Solution. The periodic time of a geostationary satellite is same as that of the Earth, i.e., 1 day or 24 hours. Exercises Q2. Sheet page 97. Answer the following question. State Newton's law of gravitation and express it in vector form. Solution. Exercises Q2. Sheet page 97. Answer the following question. What do you mean by a gravitational constant? State its SI units. Solution. Exercises Q2. XIV, page 97. Answer the following question. Why is a minimum two-stage rocket necessary for launching of a satellite? Solution. 1. For the projection of an artificial satellite, it is necessary for the satellite to have a certain velocity. 2. In a single-stage rocket, when the fuel in the first stage of the rocket is ignited on the surface of the Earth, it raises the satellite vertically. 3. The velocity of the projection of the satellite normal to the surface of the Earth is the vertical velocity. 4. If this vertical velocity is less than the escape velocity, v, the satellite returns to the Earth's surface. While, if the vertical velocity is greater than or equal to the escape velocity, the satellite will escape from Earth's gravitational influence and go to infinity. 5. Hence, a minimum two-stage rocket, one to raise the satellite to the desired height and another to provide the required horizontal velocity, is necessary for launching of a satellite. Exercises Q2. XV, page 97. Answer the following question. State the conditions for various possible orbits of satellite depending upon the horizontal speed of projection. Solution. The path of the satellite depends upon the value of the horizontal speed of projection vh relative to critical velocity vc and escape velocity v. Case I, vh less than vc. The orbit of the satellite is an ellipse with a point of projection as apogee and Earth at one of the foci. During this elliptical path, if the satellite passes through the Earth's atmosphere, it experiences a non-conservative force of air resistance. As a result, it loses energy and spirals down to the Earth. Case 2, VH equals VC. The satellite moves in a stable circular orbit around the Earth. Case 3, VC less than VH less than V. The satellite moves in an elliptical orbit around the Earth with the point of projection as perigee. Case IV, VH equals V. The satellite travels along the parabolic path and never returns to the point of projection. Its speed will be 0 at infinity. Case V, VH greater than V. The satellite escapes from gravitational influence of Earth traversing a hyperbolic path. Exercises Q3. I page 98. Answer the following question in detail. Derive an expression for the critical velocity of a satellite. Solution. The expression for critical velocity. 1. Consider a satellite of mass m revolving round the Earth at height h above its surface. Let m be the mass of the Earth and r be its radius. 2. If the satellite is moving in a circular orbit of the radius r plus h equals r, its speed must be equal to the magnitude of critical velocity vc. 3. The centripetal force necessary for the circular motion of a satellite is provided by the gravitational force exerted by the satellite on the Earth. Therefore, centripetal force equals gravitational force. Exercises Q3. Page 98. Answer the following question in detail. State any 4 applications of a communication satellite. Solution. Applications of communication satellite. 1. For the transmission of television and radio wave signals over large areas of Earth's surface. 2. For broadcasting telecommunication. 3. For military purposes. 4. For navigation surveillance. Exercises Q3. Page 98. Answer the following question in detail. Show that acceleration due to gravity at height h above the Earth's surface is. Answer the following question in detail. Discuss the variation of acceleration due to gravity with altitude. Solution. This expression can be used to calculate the value of g at height h above the surface of the Earth as long as h less than r. Exercises Q3. IV page 98. Answer the following question in detail. Draw a well-labeled diagram to show different trajectories depending upon the tangential projection speed. Solution. VH equals horizontal speed of projection. VC equals critical velocity. V equals escape velocity. Exercises Q3. B page 98. Answer the following question in detail. Derive an expression for the binding energy of a body at rest on the Earth's surface of a satellite. Solution. Exercises Q3. B page 98. Answer the following question in detail. Why an astronaut in an orbiting satellite has a feeling of weightlessness. Solution. 1. For an astronaut, in a satellite, the net force towards the center of the Earth will always be F equals mg, n. Where n is the normal reaction. 2. In the case of a revolving satellite, the satellite is performing a circular motion. The acceleration for this motion is centripetal, which is provided by the gravitational acceleration g at the location of the satellite. 3. In this case, the downward acceleration, AD equals g, for the satellite, along with the astronaut, is in the state of free fall. 4. Thus, the net force acting on astronaut will be F equals mg, mat equals 0, i.e., the apparent weight will be 0, giving the feeling of total weightlessness. Exercises Q3. B page 98. Answer the following question in detail. Draw a graph showing the variation of gravitational acceleration due to the depth and altitude from the Earth's surface. Solution. Variation of g due to depth and altitude from the Earth's surface. Exercises Q3. B page 98. Answer the following question in detail. At which place on the Earth's surface is the gravitational acceleration maximum? Why? Solution. Exercises Q3. X page 98. Answer the following question in detail. At which place on the Earth's surface is the gravitational acceleration minimum? Why? Solution. Exercises Q3. X page 98. Answer the following question in detail. Derive an expression for variation in gravitational acceleration of the Earth at with latitude. Solution. Exercises Q3. She page 98. Answer the following question. Define the binding energy of a satellite. Solution. The minimum energy required by a satellite to escape from Earth's gravitational influence is the binding energy of the satellite. Exercises Q3. She page 98. Answer the following question in detail. Obtain the formula for the acceleration due to gravity at the depth, d, below the Earth's surface. Solution. Exercises Q3. She page 98. Answer the following question in detail. State Kepler's 3 laws of planetary motion. Solution. Kepler's law of orbits. Statement. All planets move in elliptical orbits around the Sun with the Sun at one of the foci of the ellipse. Explanation. 1. The figure shows the orbit of a planet around the Sun. 2. Here, S and S are the foci of the ellipse and the Sun is situated at S. 3. P P is the closest point along the orbit from S and is called perihelion. 4. A is the farthest point from S and is called aphelion. 5. PA is the major axis whose length is 2a. PO and AO are the semi-major axes with lengths a each. MN is the minor axis whose length is 2b. MO and ON are the semi-minor axes with lengths b each. Kepler's law of equal areas. Statement: the line that joins a planet and the Sun sweeps equal areas in equal intervals of time. Explanation. Exercises Q3. XIB, page 98. Answer the following question in detail. State the formula for the acceleration due to gravity at depth, d, and altitude, h. Hence, show that their ratio is equal to, by assuming that the altitude is very small as compared to the radius of the Earth. Solution. Exercises Q3. XV, page 98. Answer the following question in detail. What is a critical velocity? Solution. The exact horizontal velocity of projection that must be given to a satellite at a certain height so that it can revolve in a circular orbit round the Earth is called the critical velocity or orbital velocity (VC). Exercises Q3. XVI, page 98. Answer the following question in detail. Show that acceleration due to gravity at height h above the Earth's surface is. Solution. Exercises Q3. XVII, page 98. Answer the following question in detail. Define escape speed. Solution. The minimum velocity with which a body should be thrown vertically upwards from the surface of the Earth so that it escapes the Earth's gravitational field is called the escape velocity (v) of the body. Exercises Q3. XVII, page 98. Answer the following question in detail. Describe how an artificial satellite using a two-stage rocket is launched in an orbit around the Earth. Solution. 1. Launching of a satellite in an orbit around the Earth cannot take place by the use of a single-stage rocket. It requires a minimum of two-stage rocket. 2. With the help of the first stage of the rocket, satellite can be taken to the desired height above the surface of the Earth. 3. Then the launcher is rotated in a horizontal direction, i.e., through 90 degrees using the remote control, and the first stage of the rocket is detached. 4. With the help of the second stage of the rocket, a specific horizontal velocity, vh, is given to the satellite so that it can revolve in a circular path around the Earth. 5. The satellite follows different paths depending upon the horizontal velocity provided to it. Exercises Q4. Page 98. Answer the following question in detail. At what distance below the surface of the Earth, the acceleration due to gravity decreases by 10% of its value at the surface, given the radius of Earth is 6,400 kilometers? Solution. At distance 640 kilometers below the surface of the Earth, value of acceleration due to gravity decreases by 10%. Exercises Q4. Page 98. Answer the following question in detail. If the Earth were made of wood, the mass of wood and Earth would have been 10% as much as it is now without change in its diameter. Calculate escape speed from the surface of this Earth. Solution. Exercises Q4. Page 98. Answer the following question in detail. Calculate the kinetic energy, potential energy, total energy and binding energy of an artificial satellite of mass 2,000 kg orbiting at a height of 3,600 km above the surface of the Earth. Given G equals 6.67 times 10⁻11 Newton meters 2 kg 2. R equals 6,400 km, M equals 6 times 1,024 kg. Solution. Exercises Q4. IV, page 98. Answer the following question in detail. Two satellites A and B are revolving round a planet. Two satellites A and B are revolving round a planet. Their periods of revolution are 1 hour and 8 hours respectively. The radius of orbit of satellite B is 4 times 104 kilometers. Find radius of orbit of satellite A. Solution. Exercises Q4. B page 99. Solve the following problem. Find the gravitational force between the Sun and the Earth. Given mass of the Sun equals 1.99 times 1030 kg, mass of the Earth equals 5.98 times 1024 kg. The average distance between the Earth and the Sun equals 1.5 times 1011 m. Solution. Exercises Q4. B page 99. Solve the following problem. Calculate the acceleration due to gravity at a height of 300 km from the surface of the Earth. M equals 5.98 times 1024 kg, R equals 6,400 km. Solution. Given H equals 300 km equals 0.3 times 106 meters, M equals 5.98 times 1024 kg, R equals 6,400 km equals 6.4 times 106 meters, G equals 6.67 times 10⁻11 Newton meters 2 kg 2. To find acceleration due to gravity at height gh. Exercises Q4. B page 99. Solve the following problem. Calculate the speed of a satellite in an orbit at a height of 1000 km from the Earth's surface. M equals 5.98 times 1024 kg, R equals 6.4 times 106 meters. Solution. Given H equals 1000 km equals 1 times 106 meters, M equals 5.98 times 1024 kg, R equals 6.4 times 106 meters, G equals 6.67 times 10 to 11 nm 2 kg 2. To find speed of satellite BC. Exercises Q4. B page 99. Solve the following problem. Calculate the value of acceleration due to gravity on the surface of Mars if the radius of Mars equals 3.4 times 103 km and its mass is 6.4 times 1023 kg. Solution. Exercises Q4. X page 99. Solve the following problem. A planet has mass 6.4 times 1024 kg and radius 3.4 times 106 meters. Calculate the energy required to remove an object of mass 800 kg from the surface of the planet to infinity. Solution. Given M equals 6.4 times 1024 kg, R equals 3.4 times 106 meters, M equals 800 kg. To find energy required to remove the object from the surface of planet to infinity equals VE. Energy required to remove the object from the surface of the planet is 1.004 times 1011 J. Exercises Q4. X page 99. Solve the following problem. Calculate the value of the universal gravitational constant from the given data. Mass of the Earth equals 6 times 1024 kg, radius of the Earth equals 6,400 km, and the acceleration due to gravity on the surface equals 9.8 meters per square second. Solution. Exercises Q4. She page 99. Solve the following problem. A body weighs 5.6 kgWt on the surface of the Earth. How much will be its weight on a planet whose mass is 1/7 mass of the Earth and radius twice that of the Earth's radius? Solution. Exercises Q4. She page 99. Solve the following problem. What is the gravitational potential due to the Earth at a point which is at a height of 2 re above the surface of the Earth? Mass of the Earth is 6 times 1024 kg, radius of the Earth equals 6,400 km and G equals 6.67 times 10 to 11 nm 2 kg 2. Solution. Given M equals 6 times 1024 kg, Re equals 6,400 km equals 6.4 times 106 meters, G equals 6.67 times 10 to 11 nm 2 kg 2, H equals 2 re.
I'm gonna set your place on fire.